Hello everyone. In this class, I will be talking about some of the basics of overcurrent relay. So overcurrent relay is one of the popular, simple, and the cheapest form of a productive device available for protecting power system apparatus. So let me give you a definition of overcurrent relay, or let me tell you when does the overcurrent relay operates. So overcurrent relay operates when the load current exceeds a preset value. So let me explain you this definition here. For that, let me take a source substation feeding a load via a feeder. As I told you earlier, relay is not directly interfaced to the system. It is connected via current transformer. So since this is an overcurrent relay, it is fed from a CT. So this is overcurrent relay. It is fed from a CT and there is a load here. Let us suppose there is a fault here and fault current is being fed in this direction. Okay. So how does this relay differentiate or understand that there is a fault? How does this relay differentiate between a normal current and fault current? So usually fault current is associated with high magnitude. We all know that, but we need to give a reference value to a relay so that it can consider any current beyond that reference current as fault current. So that reference value of current is called pickup current. Or it is called as pickup current only. So let me define you what is pickup current. Okay, pickup current is the threshold value of current above which the overcurrent relay operates. So current seen by the relay, if it is greater than the pickup current, then the overcurrent relay treats it as a fault current and it will close its strip contacts. Okay. See here, the CT is stepping down the system value of current and it is feeding to the relay. In other words, the relay coil is being fed from the CT secondary. Okay, whatever the current that is flowing in the CT secondary, that flows into the relay coil. And if that value of current, let us suppose that is called as IR. Okay, IR is the CT secondary current or the current that is flowing in the relay coil. So if that value of current IR, if it is greater than the preset value, which is otherwise called as pickup current. So this preset value is nothing but the pickup current. So if the relay coil current IR is greater than the pickup current, then relay considers this current as fault current and the relay operates. What does it mean by relay operation? Relay operation means relay closes the trip circuit. So this relay closing the trip circuit is nothing but is also termed as relay has operated. So whenever relay closes the trip circuit breaker opens and it isolates the faulty section. Okay. So to differentiate between normal current and fault current, we give a setting, we give a reference value to the overcurrent relay, and that reference value is called pickup current. So overcurrent relay is a relay which operates when the load current exceeds the preset value or pickup current. So let me further explain this. Let us suppose there is load here and there is a fault. Let us take without fault first. Let us suppose there is no fault. And this CT, for simplicity, I am taking it is a 100 by 1 ampere CT. 100 by 1 ampere CT. And we have the overcurrent relay here. And it has a it has been fed with a pickup value or reference value. Let us suppose it is 5 amperes. Okay. So 5 amperes is nothing but the I pickup. 5 amperes. Okay. So let us suppose in the line 50 amperes is flowing, that is to the load. Okay. Since it is a 100 by 1 ampere CT, IR will be, so if 100 amperes is flowing, 1 ampere will flow in the relay coil. So if 50 amperes is flowing, 0.5 amperes will flow in the relay coil. Okay. So if since here we can see that IR is less than I pickup. Okay. See, I pickup is 5 amperes. So relay will only operate when the current seen by the relay or current flowing in the relay coil exceeds this 5 amperes. Here it is 0.5 amperes, so much less than the pickup. So here relay doesn't operate. So there is an increment in the load. Load has increased, and let us suppose now the current is some 300 amperes. Okay, 300 amperes is flowing. Okay, it's just an example. Okay, 300 amperes is flowing. In the sense here, 3 amperes is coming into the relay. Okay, here in this case, so when IL, so let us consider this as load current IL. So when IL equal to 300 amperes, then relay coil current IR equal to 3 amperes. Here also 3 amperes is much less than the pickup current. IR is less than I pickup. Here also relay doesn't operate. Mind you that relay operation means relay closing its trip circuit. If trip circuit is closed, circuit breaker will act. Okay. So I will not tell the whole scenario again and again. I will just say relay operates or relay doesn't operate. Now let us suppose there is some fault. There is some fault, and due to this fault, a current of so there is some fault here, and due to this fault, a current of 1000 amperes is flowing. Okay, so pickup is 5 amperes. Here IL is, in this case, the load current flowing is 1000 amperes, right? So the current seen by the CT is 1000 amperes into the load or into the fault. 1000 amperes is flowing. Okay, the fault is here. 1000 amperes is flowing. The CT is seeing this 1000 amperes, so it will step it down. So if it is 100 amperes, 1 amperes will be flowing into the CT secondary, but here it is 1000 amperes. So to the CT secondary or to the relay coil, 10 amperes will be flowing. Okay, 10 amperes will be flowing. Here we can see that I relay is greater than I pickup. Okay, in this case, relay operates. So whenever there is a fault, the pickup is selected such that whenever there is a fault, the current flowing in the CT or the current flowing in the line exceeds this 5 amperes. So the pickup is set such a way. This is a simple operation of overcurrent relay. Now, before going any further, let me explain you. Let me tell you. Let me define you what is meant by time of operation of relay. Time of operation of relay. Time is very important here because after a fault, the protective apparatus like relay and circuit breaker has to act very fastly, and they have to quickly isolate the faulty section. We are not talking about circuit breaker here. Since we are talking about relay, let us define what is meant by time of operation of relay. Let me take you a simple overcurrent relay. Let us suppose this is an overcurrent relay. Overcurrent relay. As I told you, it is having an input. This is from CT. I'm writing it as CT from CT secondary. Also, we came to know that we will be giving it a pickup current. Pickup current. So what is its output? Its output is nothing but the trip circuit, and there is a contact inside the relay. So this is the trip circuit. Okay, there is a contact inside the relay. So whenever relay operates, this contacts will be closed. Its contacts will be closed and trip circuit will be energized. Okay. So what is meant by time of operation? Time of operation of the relay is nothing but the time instant or time lapsed between, or the time duration between the instant at which the actuating quantity exceeds pickup value. So this is one instant. So this instant is nothing but when the current seen by the relay IR exceeds the pickup, I pickup. Okay. So here IR is exceeding the I pickup. So the moment at which this happens, that is the first instant. Here see, instant at which the actuating quantity exceeds the pickup current. So here actuating quantity for an overcurrent relay is nothing but current. Okay. For an overcurrent relay, the actuating quantity is current. So when the relay current exceeds the pickup value, and so this is one instant, and the second instant is instant at which relay closes its trip contacts. So I told you that there are a trip contacts inside the relay. Whenever this relay operates, it closes its trip contacts. When trip contacts are closed, trip circuit gets energized and circuit breaker operates. So time lapse between these two instants is called time of operation of relay. This is called time of operation of since we are talking about overcurrent relay, I'm writing overcurrent relay. But for any relay, this is general definition. But for actuating quantity will be current in case of an overcurrent relay. Okay. Here in the context of overcurrent relay, I also want to define one more thing called as plug setting multiplier, PSM. Okay. PSM is given as relay coil current divided by pickup current. PSM is given is the ratio between relay coil current divided by pickup current. We all know that relay coil current is nothing but the secondary current of CT. So we can also write it as CT secondary current divided by pickup current. So why PSM is important? PSM gives the information about severity of fault. As I told you earlier, relay only operates when the fault current in the relay, when the current in the relay coil exceeds the pickup value. So we give this pickup value to a relay, and let us suppose for a particular relay, the pickup value is 5 amperes. The pickup value is 5 amperes, and this relay is being fed from CT secondary, and CT is connected to the system. Okay. So relay coil current. So inside the relay there is a coil IR. Okay. and we are giving a pickup value. So this IR depends upon the fault, right? Upon fault. As we seen here previously, see, IR is 0.5 amperes, sometimes 3 amperes. IR is 10 amperes here. So here 0.5 amperes and 3 amperes when there is no fault. But IR value increased to 10 amperes when there is a fault. So IR depends upon the current that is flowing in the to the load. So because of a fault, IR value may increase beyond the load current, right? So IR, this numerator part tells about the fault current. So this value, if the pickup is fixed to 5 amperes, we can say that PSM is proportional to IR. Okay. So if PSM equal to 1, it means that relay coil current or IR equal to I pickup, right? When PSM equal to 1. Okay. If PSM is less than 1, relay coil current, which is IR, okay, is less than I pickup. Okay. So in these both cases, so when the relay coil current is less than I pickup, relay should not operate, right? So relay doesn't operate. Why? Because relay should only operate when the relay coil current is greater than the pickup current. That is by definition, an overcurrent relay will operate only when the relay coil current exceeds its pickup. Okay. So when PSM is less than 1, it means this numerator value, which is nothing but relay coil current, which is nothing but IR, it is less than I pickup. So in this case, relay doesn't operate. But IR has increased, and it increased to a value that it is equal to the pickup current. In this case, relay is ready to operate. Relay is ready to operate. So if PSM is greater than 1, in the sense, so PSM is, I'm writing again, PSM is IR by I pickup, right? So PSM is greater than 1, in the sense IR or the relay coil current is greater than the I pickup. Okay. So in this case, the relay will operate. So it closes the trip contacts. Trip contacts are closed. Okay. So PSM greater than 1 indicates that there is a fault or the relay coil current exceeded the pickup current. Okay. So for a fixed pickup, if you fix the pickup, PSM defines or PSM shows the severity of current that is flowing in the relay coil. Okay. If the fault is more severe, more current will flow. If the fault is less severe, less current will flow. So if PSM is greater than 1, it means that IR is greater than I pickup. Okay. In other words, relay coil is experiencing more current because of a severe fault. So PSM indicates the severity of fault current. Plug setting multiplier indicates the severity of fault current. Now I have defined two things. One is time of operation of relay. Second thing is plug setting multiplier. Okay. What should be the time of operation of relay? Should it be more or should it be less? As I told you in my earlier videos, the main agenda of the protective system or system protection is to isolate the fault as quickly as possible so that least damage is caused to the power system apparatus. So we need to quickly isolate the fault. So relay has to sense the fault and quickly close the trip contacts. So the relay operating time should be time of relay should be very less, right? Okay. So let me try to plot a graph between PSM and operating time. So here PSM is nothing but IR by I pickup, right? So IR is the relay coil current, I pickup is the pickup current or the reference value above which the relay has to operate. So I will treat ISM, pickup is fixed, so ISM is nothing but IR. So when the relay coil current increases, we expect that the relay should operate quickly. So relay coil current is increasing. So let me draw the same figure. Okay, there is a fault here. So this is the relay. We have a CT here. Okay. So there is one fault here, which is causing. Let take the no fault case first. Let us take the no fault case first. So when there is no fault, this relay will not operate. So when there is no fault, in the sense the current seen by this relay IR is less than its pickup value. So when there is a fault, let us suppose the current drawn is 600 amperes. Okay, 600 amperes, and the pickup is 5 amperes for this relay. I pickup is 5 amperes. So this is case 1. Okay, so here again I'm taking the same 100 by 1 ampere CT. Here IL, the current flowing into the load is 600 amperes. Okay, I pickup we have as I pickup as 5 amperes. So what will be the IR? IR, so 100 amperes flowing in the line, 1 ampere will flow into the CT secondary. So IR 600 amperes is flowing, so we have 6 amperes. So this is one case. In the second case, let us suppose instead of 600 amperes, 1000 amperes is flowing. Okay, so here IL equal to, because of the fault, okay, 1000 amperes, but I pickup is fixed, that equal to 5 amperes. So IR equal to 10 amperes, right? So because here in the second case the fault is more severe, so 10 amperes or in the line 1000 amperes is flowing, and its reflected value 10 amperes is flowing in the relay. When you compare these two cases, PSM value will be higher in case 2. So this is case 1, and in case 2 PSM value will be higher, because in both the cases the pickup is 5 amperes, the pickup is fixed at 5 amperes, and here the numerator value IR is 6 amperes here and 10 amperes here. Okay, so the bigger the numerator on the second case, in the second case, so PSM value will be higher. So PSM is nothing but an indicator of magnitude of IR. So we can, while plotting, let us assume that here IR is present. Okay, so in the second case the fault is more severe when compared to the first case. In the second case, we expect the relay to operate faster, so that the less damage is caused. I told you the time for which the fault persists in the system, okay, decides the damage cost. Okay, because the heat produced because of the flowing fault current depends upon the time for which the fault current persists. So we need to quickly isolate. Okay, so we expect the relay to operate more faster in this case when compared to this case. So the time of operation of a relay should be inversely proportional to the fault current. Here fault current is 1000 amperes in second case, and first case it is 600 amperes. But relay is not exactly seeing the fault current, it is seeing the current stepped down by the relay, stepped down by the current transformer. Okay, so for relay fault current is the 6 amperes in this case, 10 amperes in this case. Okay, its pickup is 5 amperes, right? So both the cases the relay will operate. Both 6 amperes and 10 amperes, relay will treat it as fault current only. But since 10 amperes is more dangerous current, relay has to operate faster when compared to the 6 amperes case. So we expect a inverse relation between time and PSM. So we should, somewhere the graph should be something like this. There should be an inverse relation between time of operating time and PSM. In the sense, as the fault magnitude increases, the operating time of the relay should come down. Okay, so that is the desired characteristics between time and current, relay coil current. So PSM can be treated as relay coil current. That is one more important observation that we need to make while studying overcurrent relays. So far I told you what is meant by overcurrent relay. I have defined you what is meant by preset pickup current. Pickup current is nothing but the value of current above which the relay operates. I have also told you the time of operation of relay, and I have defined you PSM. So PSM is nothing but the relay coil current by pickup current, and we have tried to plot a graph between PSM and operating time. So just keep this one in mind. We will come across this kind of characteristics while studying this overcurrent relay. As you further proceed, we will come across these characteristics. I need to tell you a few more things before closing this lecture. Those are torques inside a relay. Operating torque and a restraining torque. If you watch the basic operation of relay and circuit breaker, in that video I have explained you what are these torques. So again I'm trying to define here. Operating torque, this is the torque responsible for closing the relay trip contacts, relay contacts. So this is a torque that is produced inside the relay, and that is trying to close the relay contacts or trying to make the relay to operate. So this makes the relay to operate. So the relay operation means relay is closing the trip contacts. So that whole thing is called as relay operation. Okay, operating torque is trying to make the relay to operate. It is trying to close the trip contacts. Okay, operating torque is produced in electromagnetic relays by attraction, electromagnetic attraction. So electromagnetic attraction or electromagnetic induction. Okay, so we are using electromagnetic attraction or electromagnetic induction to produce the operating torque inside an electromagnetic relay. So restraining torque, it has two functions. I told you. It opposes the, so by nature it opposes the operating torque. Operating torque. So operating torque is making the relay to operate, whereas restraining torque is opposing the relay operation, right? So what are its two functions? The first function is we need the relay to operate only when the current in the relay exceeds the pickup value, right? But when the current is below the pickup value, the relay should not operate. So there should, but when the current is below pickup value also, there is an operating force or operating torque within the relay. When the current is below the pickup value also, there is an operating torque. What operating torque is doing? It is making the relay to operate. But relay should not operate when the current is below pickup, because there is no fault when there is no pickup. When the current is below pickup, there is no fault in the system. So there is an operating torque even though there is no fault on the system. So to counter this operating torque, we are introducing a restraining torque. So restraining torque here is restraining the, restrain means suppose restraining the relay operation under no fault condition, under no fault condition. In the sense, when there is no fault, there is a counter torque to the operating torque called restraining torque, and that is opposing the relay operation when there is no fault. Exactly when fault occurs, let us call it as T op and TR. So when the fault occurs, the operating torque just exceeds the restraining torque. Okay, this happens under fault condition. Or I can say when the relay coil current exceeds the pickup current. So fault is external to the relay, and relay only sees this condition. It senses only this condition. Whether there is fault or there is no fault, whether there is a severe fault, whether there is a low magnitude fault, it doesn't matter to a relay. What all matters to an overcurrent relay is just its pickup value and its current value. So if when the current seen by the relay just exceeds the pickup, then the relay will operate. Why it will operate? Only this condition, because internally this is happening. The operating torque inside the relay is greater than the restraining torque. So this is happening only when there is a fault. But when there is no fault, the restraining torque dominates. This is under no fault condition. This is under no fault condition. So when there is no fault, the restraining torque is greater than the operating torque, and the relay restrains its operation. In the sense, relay doesn't operate when there is no fault because of the presence of restraining torque. Restraining torque is also having one more purpose. So it brings back the relay contacts to initial position after circuit breaker has cleared the fault. I have explained you about this point already when I have explained the basic operation of a relay and circuit breaker. Okay, once the relay has operated, let me take you to the diagram quickly. So here we are having a circuit breaker whose contacts are normally closed. This is a trip circuit. We are having the trip contacts here, and there is a plunger here, right? This is the CT. Okay. This is the relay coil, right? So when there is a fault here, the current seen by the relay IR, so IR exceeds the I pickup. So this is happening when there is a fault. So when this happens externally to the relay, so external to the relay there is a fault and IR just exceeded the pickup value. Then internally inside the relay, the operating torque exceeds the restraining torque. So there is a restraining torque here, there is a spring here which is pulling this plunger in this direction. Whereas the magnetic attraction due to the relay coil is pulling the plunger in this direction. So here we are having contacts A and B. If these two contacts A and B are bridged by this plunger, the trip circuit is closed. So this is trip circuit. I have explained this already in my earlier videos. The trip circuit is closed. If trip circuit is closed, this coil gets energized. If this coil gets energized, this moving contact of the circuit breaker is pulled in this direction. Okay. So that happens when there is a fault. T operating is greater than restraining torque, and then what happens is relay operates. Relay operates. In the sense A and B are closed. A and B contacts are closed. That is nothing but trip circuit is energized. This is happening when the relay operates. So when A and B are closed, CB will open. Circuit breaker will open. Okay. When circuit breaker will open, what happens is, see, when CB will open, so there is an open circuit here, right? See, circuit breaker has opened. So we will have this diagram like this. Okay. So there is an opening here. So when there is an opening here, what happens to the relay coil current IR? So relay coil current IR equal to 0. Okay. So then relay coil current IR is, since it is 0, because there is an opening, the fault is not being fed now, as well as the relay is also not seeing any current. So IR is less than here I pick up because IR is 0. So in this case, what happens? When IR is less than I pick up, restraining torque dominates the operating torque. After all, operating torque here is produced by magnetic attraction. See, IR is essentially flowing in the relay coil and it is attracting this plunger towards the contacts C and B. So this magnetic attraction is creating the operating torque here. For this magnetic attraction to happen, there should be some IR, but here IR is 0. So T operating torque is also 0. So if IR is 0, operating torque is also 0. Whether it is a magnetic attraction or magnetic induction, current is necessary for creation of flux. When there is no current, there is no flux, and when there is no flux, there is no torque. Okay. So the operating torque is 0 and restraining torque dominates. Restraining torque dominates. Then what happens is that relay contacts A and B will open. A and B will open. In the sense, this plunger will be pulled back to its normal position. When there is a fault, A and B are closed. This plunger was pulled in this direction. But when the trip circuit is closed, circuit breaker has opened. Once circuit breaker opens, the relay contacts A and B will open, or relay will reset. We can also say relay will reset to its normal position. This is happening because of the presence of restraining torque TR, which is produced by this spring here. So that is the second function of the operating torque. So there are two torques inside a relay. One is operating torque and restraining torque. Restraining torque is trying to oppose the relay operation, whereas operating torque is trying to make the relay to operate. Restraining torque restricts the relay operation under no fault condition. Obviously, this is the most desired thing. A relay should not operate when there is a fault. The second thing is that restraining torque is helping to reset the relay once the circuit breaker clears the fault. In the sense, circuit breaker opens and the fault current is no longer being fed, then the relay comes back to its original position because of the presence of restraining torque. The last thing that I want to mention here is current setting and time setting in overcurrent relays. See, as I told you that overcurrent relay, let's suppose this is overcurrent relay. So it is being fed from CT, and its output is nothing but its contacts, right? So once the relay operates, these contacts are closed and trip circuit is energized, right? And I told you that we have a reference value given here called pickup, and we can adjust this pickup. We can change this pickup. Why to change pickup and how to change, that we will try to understand in the upcoming lectures. But we can change this pickup value by using current setting. Okay, current setting is used to change the pickup current of relay. And I also defined you what is meant by time of operation of relay, right? We can also adjust the time of operation of relay by using time setting. So time setting is used to adjust the time of operation of relay. You might ask me, like, we desire the relay to operate at lowest possible time. Why to adjust it? Why to increase or decrease it? Well, that might if that really strike in your mind, I appreciate it. I will try to explain that in my upcoming lectures why it is necessary to adjust the time setting of the relay, adjust the time of operation of the relay, increase or decrease the time of operation of relay. So time setting helps to change or adjust the time of operation of relay, time of operation of relay. So I'm now erasing this I pickup, and I'm just putting it as current setting here, current setting, because by giving this setting we are nothing but changing or increasing or decreasing the pickup current. So this is the pickup current setting. Current setting is nothing but we are adjusting the pickup at which the relay operates. So we have here something called as time setting also. Time setting. So this is a block diagram of overcurrent relay. Okay, it is being fed from the current transformer secondary. It closes the trip contacts when it operates. For it to operate, we give a reference value called pickup current, which can be adjusted by the current setting feature of the overcurrent relay. Once the current exceeds the pickup value, the relay operates to close the trip contacts. Okay, so the time taken by the relay also can be adjusted by using the time setting feature of the overcurrent relay. So that's all about overcurrent relay for this lecture. In the upcoming lectures, I will talk about what is the need for changing time setting and current setting. Thank you.